Right now, 10 metric tons of complex carbon-rich material is violently plummeting out of Saturn's orbital rings and burning up into the gas giant's upper atmosphere every single second. This torrential downpour of cosmic matter is happening on a scale so massive that it fundamentally alters the timeline of our solar system, essentially putting a definitive ticking clock on the lifespan of the most iconic planetary feature we know. But believe it or not, this evaporating ring system is far from the most disorienting revelation currently emerging from a hard drive of supposedly finalized space telemetry. You see, back in the autumn of 2017, a robotic explorer was intentionally incinerated in the skies of an alien world, effectively ending its decades-long mission. The world moved on. The scientific books were seemingly shut. Yet, as we sit here in the middle of this decade, fresh analyses of that exact same archived telemetry are publishing findings so utterly counterintuitive that they are forcing astrophysicists to tear up their foundational textbooks. We are not talking about some simple software update making old photographs look slightly sharper. We are looking at peer-reviewed papers that challenge our basic comprehension of magnetic fields, subterranean oceans, and the fundamental building blocks of biological life. And to understand the puzzle that researchers are desperately trying to piece together today, we have to look back at a machine that refused to stop teaching us, even long after its physical body ceased to exist. To truly grasp the magnitude of these contemporary breakthroughs, you must first understand the unprecedented scale of the engineering marvel that made them possible. The robotic explorer known as Cassini was not merely a probe. It was arguably the most complex, heavily instrumented piece of interplanetary hardware ever successfully deployed by our species. When it violently tore through Earth's atmosphere on a Titan IV rocket in the late 1990s, it carried a sprawling suite of sophisticated sensors, alongside an atmospheric lander destined for a hazy alien moon. It spent the better part of 7 years utilizing the gravitational pull of Venus, Earth, and Jupiter to slingshot its way across the cold vacuum, finally inserting itself into the Saturnian system in the middle of 2004. For more than a decade, it operated as humanity's unblinking eye in the outer darkness. It mapped invisible magnetic forces, charted liquid hydrocarbon lakes under thick orange smog, and captured hundreds of thousands of high-resolution images that transformed a distant point of light into a dynamic, shifting neighborhood of fascinating worlds. But as the fuel reserves inevitably dwindled after 13 years of continuous orbital maneuvers, mission controllers faced a grim ethical dilemma. Allowing a derelict, unpowered machine to blindly drift through the system risked a catastrophic collision with pristine moons that might harbor subsurface environments. Planetary protection protocols dictated a clean, controlled disposal. So they engineered a spectacular death. During its final 5 months, controllers commanded the spacecraft to execute 22 white-knuckle trajectories straight through an unmapped, treacherous void. This was a narrow, terrifying corridor spanning barely 2,000 miles, located directly between the planet's lethal upper atmosphere and the inner edge of the razor-sharp ring debris. It was a region of space absolutely untouched by any human-made artifact. During these terminal orbits, every single onboard instrument was commanded to run at absolute maximum capacity. The probe was sniffing, tasting, and measuring a completely alien environment at blistering speeds, continuously beaming raw zeros and ones back toward terrestrial antennas. When the machine finally plunged into the crushing pressures of the planet's atmosphere and was torn apart at a molecular level, the raw telemetry was carefully stored away in digital vaults. The general public assumed the era of discovery had concluded. But here is where the narrative takes a sharp turn, because the data harvested during those harrowing final passes was so incredibly dense, so overwhelmingly rich in microscopic detail, that the analytical software of 2017 simply could not fully process it. It required nearly a decade of advancements in data science, coupled with entirely new theoretical frameworks, to finally decode the whispers hiding in that archived static. And what those archives are revealing right now is nothing short of a paradigm shift. Perhaps the most staggering revelation to surface from this digital excavation concerns a tiny, blindingly white satellite named Enceladus. By late 2025, researchers utilizing vastly upgraded analytical models began scrutinizing the historical readouts collected when the spacecraft flew directly through the icy plumes erupting from this moon's southern pole. Previously, we understood that these geysers contained water vapor, simple salts, and traces of basic organic material, hinting strongly at a vast, dark, liquid ocean churning miles beneath the frozen crust. That alone was a monumental discovery for its time. But when a dedicated team of researchers recently subjected the archived mass spectrometry data to cutting-edge computational analyses, the chemical signature they uncovered was exponentially more complex than anyone had dared to anticipate. The newly deciphered telemetry proved that this subterranean sea was not merely a passive reservoir of salty water, it was actively churning out highly complex, heavy molecular structures. We are talking about the definitive identification of esters, ethers, alkenes, and intricate compounds bearing both nitrogen and oxygen. Why does this specific vocabulary matter so much? Because in the realm of biochemistry, these are not just random assortments of space dust. These exact chemical architectures represent the fundamental precursors to lipids. On our home planet, lipids are the crucial structural components that biological life utilizes to construct cell membranes. They are the microscopic walls that separate a living organism from its surrounding environment, allowing complex, self-sustaining biological reactions to occur in isolation. To be absolutely clear, researchers are meticulously pointing out that detecting these membrane-building blocks is not the same thing as detecting living microbes. No one is claiming that alien fish are swimming in the dark waters of Enceladus. But the sheer existence of these heavy, undegraded chemical chains proves something almost equally profound. It demonstrates that the chemical engine operating beneath that icy shell is intensely active, highly energized, and capable of spontaneously assembling the exact molecular structures that life requires to take hold. Furthermore, the telemetry confirms these heavy organics were identified in remarkably fresh plume material, completely refuting the earlier assumption that complex compounds in the Saturnian system were just ancient, irradiated debris slowly baking in the vacuum of space. These molecules were freshly cooked, they were recently synthesized, and they were aggressively venting straight out of an alien ocean directly into the crosshairs of a falling spacecraft. Trying to mentally map this biochemical reality onto a frozen, distant rock deeply challenges our terrestrial intuition. When you think of environments capable of synthesizing the precursors to living cells, you naturally picture warm, sun-drenched tidal pools or rich oxygenated atmospheres bathed in steady solar radiation. Now imagine taking a celestial body small enough that you could comfortably nestle its entire landmass within the geographic borders of the American Midwest. Cover this tiny sphere in a jagged layer of ice miles thick, plunging the surface temperature to hundreds of degrees below zero. Finally, push this frozen ball nearly 1 billion miles away from the sun, where the available solar energy is a mere fraction of a percent of what we receive here on Earth. Logically, a place like this should be a geologically dead, utterly silent tomb. But physics offers a violent alternative to sunlight. Think about what happens when you take a thick metal paperclip and rapidly bend it back and forth between your fingers. Within seconds, the friction at the joint generates enough heat to burn your skin. This is roughly the mechanical reality of tidal heating. As this diminutive moon races around its colossal host planet, the immense, inescapable gravity of the gas giant relentlessly stretches and squeezes the moon's rocky core. This continuous, brutal deformation generates phenomenal amounts of internal friction. That deep grinding heat is what melts the inner ice, sustaining a global, pitch-black ocean. And at the very bottom of this abyssal sea, where the hot, fractured rock meets the freezing, high-pressure water, something extraordinary happens. To understand it, we have to look at the deepest, most inaccessible trenches of our own oceans, specifically at geological formations known as hydrothermal vents. In these lightless terrestrial depths, scorching mineral-rich fluids spew from the crust, interacting with the surrounding seawater to drive wildly complex chemical reactions. These deep-sea terrestrial chimneys are absolutely teeming with bizarre, resilient ecosystems that operate entirely independent of solar energy, surviving purely on chemosynthesis. The archived telemetry suggests that this exact same thermodynamic engine, the violent meeting of hot rock and cold liquid, is currently running at full capacity on a frozen moon in the outer darkness. The spacecraft essentially flew past an extraterrestrial exhaust pipe and caught a face full of freshly manufactured cell membrane ingredients, proving that the exact same factory floor that might have birthed life on our planet is currently open for business 1 billion miles away. How exactly does a robotic probe traveling at orbital velocities manage to positively identify microscopic molecular chains suspended in a vacuum? The answer lies in a brilliant piece of engineering known as a time-of-flight mass spectrometer, specifically integrated into the probe's dust analysis hardware. When the spacecraft brutally punched through the erupting geysers or grazed the outer edges of the planetary rings, It was impacting microscopic grains of ice and dust at velocities exceeding tens of thousands of miles per hour. At those extreme collision speeds, the tiny particles do not simply bounce off the hull. They are violently shattered and instantly vaporized into a cloud of charged ions. The onboard instrumentation then utilizes an electrical field to aggressively pull these newly formed ions down a tightly controlled sensor tube. Here is where the fundamental physics of mass comes into play. If you apply the exact same electrical pull to a variety of objects, the lighter ones will invariably accelerate faster and hit the detector at the end of the tube much sooner than the heavier, bulkier objects. By meticulously recording the precise microsecond that each ion strikes the target plate, the computer can calculate the exact atomic weight of the particle. It is essentially a high-speed subatomic sorting machine. For years, analysts examining the initial readouts saw a jumbled, chaotic graph of weights that mostly corresponded to simple water molecules, carbon dioxide, and basic ammonia. But here's the critical pivot that occurred during the recent re-examinations. Modern algorithms, benefiting from years of laboratory advancements and machine learning techniques, were finally able to filter out the background noise of the collision data. They began separating the chemical signatures of old, heavily irradiated dust grains that had been circulating in the rings for centuries from the signatures of pristine, newly ejected ice crystals that had just rocketed out of the subterranean ocean minutes prior. When researchers isolated the data specifically belonging to those fresh, undegraded ice grains, the mass graphs spiked in entirely new, heavier weight classes. The mathematical profiles matched the complex laboratory signatures of esters and ethers with terrifying precision. It was not a malfunction, and it was not a loose interpretation of blurry data. The physical weights of these chemical chains are an inescapable mathematical reality, recorded by a machine that was meticulously designed to never lie. While the biological implications of the icy moons continue to dominate headlines, the archived data from the spacecraft's ultimate suicide dives through the atmospheric gap produced a physical anomaly that is currently tearing the planetary physics community apart. When the machine threaded the needle between the rings and the atmosphere, its magnetometers mapped the gas giant's internal magnetic field with unprecedented, point-blank clarity. What they recorded shouldn't actually exist. According to every established model of planetary geodynamos, a massive planet generates its magnetic shield through the chaotic churning of conductive fluids deep within its interior. On Earth, this is liquid iron. On a gas giant, it is deeply compressed, metallic liquid hydrogen. For this churning fluid to generate a sustainable planet-wide magnetic field that lasts for billions of years, the axis of the magnetic field must be distinctly tilted away from the planet's actual axis of physical rotation. This slight offset is absolutely mathematically mandatory for the dynamo to keep regenerating itself. If the magnetic pole and the rotational pole perfectly align, the entire magnetic field should rapidly decay and collapse into nothingness. Yet, the terminal telemetry proved that this planet's magnetic field is aligned with its rotational axis to a staggering degree of precision, showing a tilt of less than 1/10 of a single degree. It is unnervingly, impossibly perfect. Astrophysicists are struggling to explain how this is physically viable. Some theorists are frantically proposing that a thick, undiscovered layer of raining helium deep inside the planet is acting like a massive internal cloak, somehow masking the true tilted magnetic field from our sensors. Others are taking a much harder stance, arguing that our fundamental understanding of how fluid dynamics generate magnetic fields on a cosmic scale is simply unequivocally wrong. And if that wasn't enough to scramble our models, the final pass has also quantified the legendary ring rain. We always theorized that the rings were slowly degrading, but the close-range sensors measured a catastrophic hemorrhage. 10 metric tons of intricate carbon-heavy molecules are draining out of the ring plane every single second. At this ferocious rate of decay, the grandest visual spectacle in our night sky is not a permanent fixture. It is a fleeting, temporary phenomenon that will likely be completely erased from existence in less than 100 million years, which is barely a blink on the cosmic timeline. But let's pause here because it is crucial to recognize that the scientific method does not solely exist to validate our wildest, most optimistic hypotheses. True science is a ruthless, self-correcting mechanism, and the exact same historical archives that provided evidence of a biologically promising ocean on one moon have systematically dismantled our assumptions about another. For decades, the massive, hazy satellite known as Titan was the undisputed crown jewel of outer solar system astrobiology. It is larger than the planet Mercury. It possesses a thick, choking atmosphere composed mostly of nitrogen, and its surface is uniquely carved by flowing rivers and vast lakes of liquid methane and ethane. Based on early gravity measurements and orbital mechanics, The consensus among researchers was practically rock solid. Deep beneath its frozen, organic, rich outer crust, there had to be an incredibly deep global ocean of liquid water, and it simply made too much sense. The heat generated by the moon's massive internal core, combined with its orbital dynamics, meant that a subsurface sea was treated as an almost guaranteed factual baseline in astronomical literature. However, late in 2025, a brilliant reevaluation of the spacecraft's historical gravity assist data brought that entire theoretical framework crashing down. By applying newly developed models to the tiny, subtle shifts in the probe's velocity as it swung past the hazy giant years ago, researchers realized that the internal density of the moon did not match the profile of a sloshing liquid interior. The updated calculations strongly suggest that the internal structure is likely a heavily mixed, rigid concoction of rock and ice extending deep into the core, explicitly lacking the distinct separated layer of liquid water we all assumed was there. Does this mean the hazy moon is suddenly boring? Absolutely not. Its surface chemistry remains one of the most complex, alien environments we have ever observed, but the sudden evaporation of its theoretical subsurface ocean serves as a harsh, vital reminder. The universe is under zero obligation to conform to human expectations. We can build the most elegant, logical models imaginable, but if a fresh look at the hard data mathematically contradicts those models, the models must be discarded. The archives are proving to be just as effective at destroying old dreams as they are at creating new ones. Yet, in a beautiful stroke of cosmic irony, exactly as the data stripped a hidden ocean away from one of the largest bodies in the system, it unexpectedly gifted a brand new one to a moon that everyone had completely written off as geologically dead. Enter Mimas. This is a remarkably small, heavily battered chunk of ice that is instantly recognizable to anyone who has ever seen a science fiction movie, largely because a colossal impact crater on its surface makes it look exactly like a certain heavily armed space station. Visually, this moon exhibits zero evidence of internal activity. There are no smooth, resurfaced plains. There are no erupting geysers. There are no stress fractures carving through the ice. It is utterly saturated with ancient impact craters, which is the universal hallmark of a frozen, inactive rock that hasn't experienced geological renewal in billions of years. But in early 2024, a team of researchers decided to meticulously review the archival records of the moon's orbital libration. Libration is essentially a measurement of how much a celestial body physically wobbles or rocks back and forth on its axis as it travels along its orbital path. Think about what happens when you try to spin a hard-boiled egg on a kitchen counter versus spinning a raw egg. The hard-boiled egg, being completely solid inside, spins uniformly. The raw egg, however, contains a sloshing liquid interior that violently disrupts its momentum, causing it to wobble erratically. When scientists processed the old positional telemetry, they discovered that the cratered moon was wobbling identically to the raw egg. The crust is physically detached from the solid core, floating on top of a dynamic, shifting layer of liquid water. And because the surface ice remains completely unfractured, orbital dynamics dictate that this hidden sea must be incredibly young, likely forming a mere 5 to 15 million years ago. In geological terms, that is quite literally yesterday. We are looking at a newborn ocean, gestating entirely undetected beneath a scarred ancient shell discovered completely by accident in data that was recorded years before anyone even conceived of the correct mathematical questions to ask. The sheer volume of these retroactive discoveries is rapidly shifting the trajectory of global space agencies. In December of 2025, yet another comprehensive review of the terminal dive data revealed that the majestic flat rings we have admired through telescopes for centuries are actually surrounded by a massive, invisible halo of electrically charged dust. This unseen cloud extends radically outward, reaching 3 times the radius of the planet itself above and below the visible ring plane. It completely eluded every terrestrial telescope because you fundamentally cannot see it. You can only detect it by physically flying a sensor through it. These relentless revelations have catalyzed a massive pivot in the focus of modern astrobiology. The historical search for habitable zones used to strictly revolve around finding rocky planets situated at the precise, warm distance from a star where liquid water could pool on the surface. Today, the conversation is entirely dominated by a new classification: ocean worlds. Because of the archived telemetry, space agencies now recognize that the most biologically promising real estate in our solar system might actually be located in the freezing, lightless outer domains, locked safely beneath miles of protective ice. This is no longer purely theoretical planning. NASA's Europa Clipper is actively hurtling through the vacuum right now, heading toward the Jovian system to apply the exact same investigative techniques to Jupiter's icy satellites. Meanwhile, the European Space Agency has fundamentally elevated the geyser-erupting Saturnian moon to its absolute highest priority tier for future exploration. Conceptual frameworks are already being drafted for specialized landers capable of touching down directly on the fractured southern crust, tasked with actively sampling the fresh chemical fallout on the surface rather than attempting to catch fleeting particles at orbital velocities. The era of just taking pictures is over. The era of direct molecular sampling in the outer solar system has officially begun, and it was entirely triggered by a hard drive full of old zeros and ones. There is a specific haunting detail about the conclusion of this mission that perfectly encapsulates why we continue to explore. On the morning of September 15, 2017, the very last stream of telemetry successfully reached the massive receiver dishes here on Earth, but because of the immense crushing distances involved in interplanetary communication, radio waves traveling at the absolute speed of light still required exactly 83 minutes to cross the vast gulf between Saturn and our home planet. For nearly an hour and a half, the mission control room sat in absolute silence, watching their monitors display a steady, unbroken stream of pristine data detailing the magnetic anomalies, the microscopic ring dust, and the atmospheric chemistry of an alien world. During that entire 83-minute window, the robotic explorer sending that information no longer physically existed. It had already been completely vaporized, melted down into its constituent atoms in the crushing pressures of the gas giant. The data was flowing from a ghost. The machine was dead, but its voice was still traveling through the dark. And in a profoundly real way, that voice has never actually stopped echoing. As we push deeper into the late 2020s, utilizing computational tools that the original engineers could barely have imagined, we are still listening to that exact same transmission. We sent a machine into the absolute dark equipped only with the tools to measure what we expected to find. Instead, it sent back a sprawling, chaotic puzzle featuring actively vanishing rings, impossible magnetic fields, newborn subterranean oceans, and the intricate chemical precursors to biology venting into the vacuum. The final dive did not close the book on the outer solar system. It merely provided us with a new dictionary, and we are finally learning how to read the words.